Hello everyone, and welcome back to another chapter of our Physics O-Level lessons. Today is our 6th chapter and we're going to be learning about waves and sounds. In waves and sounds, we're going to learn transverse waves, longitudinal waves, how we describe waves. We're also going to learn the wave equation, and then we're going to learn reflection, refraction and diffraction. To see how we display sounds, what is the speed of sounds, the refraction of sounds, what is frequency and pitch, and lastly ultrasound and echo sounding. So let's begin this chapter by first describing waves and sounds. If you drop a stone into a pond, ripples spread across the surface. Like you can see this ripple, a drop of water hit the surface of this liquid, and tiny waves started to form. These tiny waves carry energy, and as you can tell from the movement, they cause at the water's surface. But there is no flow of water across the pond, and no matter is transferred. So this wave effect is just the result of up and down motions in the water. So waves are not only found on water. Sound travels as waves as well, and so does light. Waves can also travel along stretched springs, and these show that there are two main types of waves. Let's look at them right away. The two main types of waves are the transverse waves and the longitudinal waves. First, we're going to look at transverse waves. Here we have a slinky spring. So when the end coil of this spring is moved sideways, which means this motion, here and then here and then here, like this. So when the coil of this spring is moved sideways, it pulls the next coil sideways a fraction of a second later, and so on along the spring. In this way, the sideways motion is passed from coil to coil, and a traveling wave effect is produced. So as you can see, the to and fro movements of the coils are called oscillations. These are the movements we're talking about. This is the direction of the wave traveling. So if we start moving the coil from here at this point, the wave would travel in this direction. So when the oscillations are up and down or from side to side, the waves are called transverse waves. In transverse waves, the oscillations are at right angles to the direction of travel. By this we mean that the direction of this wave in the spring is in this direction, the direction this arrow represents. And in transverse waves, the oscillations, these are the oscillations, are at right angles to the direction of the travel. They are not within this angle. They are to the right angle of this direction of travel. Light waves are transverse waves, although it is electric and magnetic fields which oscillate rather than any material. So this was transverse waves. I hope you have understood it. You may understand much more when we look at longitudinal waves, because longitudinal waves are different from transverse waves. So if we move the end coil of the spring backwards and forwards, which means we push it and then pull it, this movement also produces a traveling wave effect. However, the waves are bunched up sections of coils with stretched out sections in between. These sections are known as compressions and rarefactions. So the bunched up section are called the compression, and the stretched out sections in between are called the rarefactions. Basically, when we push the spring and pull it in the direction of travel of the wave, then we get a longitudinal wave. So you can see that these longitudinal waves are different from transverse waves. Transverse waves have side-to-side movements, like a wave kind of effect, like a wave movement. But in longitudinal wave, we have compressions and rarefactions. So when the oscillations, transverse waves have a shape like this. They are moved from side to side, and they make up a wave shape like this. They don't have compressions or rarefactions. The oscillations of these waves are up and down, or from side to side. But In longitudinal waves, the oscillations are backwards and forwards. So in longitudinal waves, the oscillations are in the direction of travel. They're not at right angles to the direction of travel. They are in the direction of travel. You can take sound as an example of such a wave. Sound doesn't have a transverse wave. Sound has longitudinal waves. So that is why when we listen to a note of guitar, we might feel compressions and rarefactions in the sound. Alternating compressions and rarefactions we hear as well. These were longitudinal waves and transverse waves. They were pretty simple, but we have to learn how we can differentiate these two. And I've also told you the differences between these waves. Now let's look at properties of the waves. Firstly, we have the speed. So the speed of the waves is measured in meters per second. This is the equation of speed, m divided by s. And we have frequency as well. The SI unit of frequency is the hertz. The symbol of the hertz is Hz. For example, if we make 4 oscillations per second with the spring, then 4 waves pass any point per second, and the frequency is 4 hertz. So the time for one oscillation is called the period, and this is equal to 1 divided by frequency. So the frequency is 4 hertz, the period is 1/4 second. So then we have wavelength. Wavelength is the distance between any point on a wave and the equivalent point on the next. Here, let me show you. This is the wavelength from one crest to the other crest, or the distance from one compression to the other is called the wavelength. And then lastly we have the amplitude. This is the maximum distance a point moves from its rest position when a wave passes. So a wave is something like this. You can see it over here. This is a wave. So the magnitude of this wave would be the height of this wave from this rest position to the top. What is the height of the wave? This tells us the amplitude. Now let's move ahead on to understanding the wave equation. The speed, frequency, and wavelength of any set of waves are linked by this equation. We have speed is equal to frequency multiplied by wavelength. And in symbols we write it as V is equal to F into lambda. This sign is called lambda and it represents wavelength. So speed is measured in meter per second, frequency is measured in hertz, and wavelength in meters. So let's see how this equation works using this example. So these waves, as you can see, are traveling across water. Each wave is 2 meters long. So the wavelength is 2 meters from one crest to the other. So how do we measure this wavelength? We find out the crest of the wavelength, which is this point, and from this point we go to the next crest of the wavelength, which is this point. So this is the wave that we're going to be measuring. So the wavelength is 2 meters. 1 second later, 3 waves have passed this flag. So the frequency is 3 hertz. So the waves are 3. There are 3 waves that have been passed from this flag in 1 second. So frequency is equal to waves multiplied by second, and we get 3 hertz. So we get 3 hertz. So the waves have moved 3 wavelengths. So if we multiply 3 by 2 meters, 3 is the number of waves and 2 meters is the wavelength of a single wave. So we multiply 3 by 2, so we get their speed 6 meters per second. So this is how it worked. The equation, speed is equal to frequency into wavelength. We just multiplied the frequency of the waves with the wavelength of a single wave, and we got their speed, 6 meters per second. So this is how this equation is used. Whenever we are given frequency or wavelength, we can find out the speed of this wave. If we are given the speed or frequency, we can find the wavelength. So we can remember the rearranging triangle I taught. In this triangle, we put these two values below this value, speed upon frequency into wavelength. This is going to be the triangle. Now if we want wavelength, we would hide the wavelength, and what we get is speed divided by frequency. And if we hide the frequency, which means that we want the frequency, then we get speed divided by wavelength. And if we want speed, we multiply frequency with wavelength. So we can think about that triangle whenever we have to rearrange this equation in order to find another value, wavelength or frequency. So I hope you have understood the wave equation well, so we can move ahead on to wave effects. What are the effects of waves? So the properties of waves can be studied using a ripple tank. So here we have a ripple tank. The ripple tank has a shallow water tray which is suspended by these legs. We have a lamp above it. So what happens? When we turn on this lamp, we get a shadow of the water beneath the tray on the ground. So we have two types of dippers which make two different types of waves. These waves are called ripples. By ripples we mean tiny waves, so they are small. We have a plane dipper which makes plane waves, and then we have another dipper which makes radial waves. So these are circular. Like when we see a drop of water falling onto the surface of water, the waves sent out are radial, not linear. So we have two different types of waves. We have linear waves and we have radial waves. Radial waves. And we have radial waves. So the two dippers make the two different types of waves. So the dipper vibrates and it sends out waves on the water surface. Then obstacles are put in the wave's path to see what effects are produced. So now we're going to look at the first effect of waves. This is reflection. So when a vertical surface is put in the path of the waves are reflected from the surface at the same angle as they strike it. So if the waves are in this angle when they strike the block, they go off in the same angle but in the opposite direction. So this is reflection. As you can see, the waves overlapped each other at this point and we can see it. So this is reflection of waves. The next effect the waves produce is the refraction. So a flat piece of plastic makes the water more shallow, which slows the waves down. So when the waves slow, they change direction, and this effect is called refraction. So we have no object over here, it's just plain water. But at this point we have put a piece of plastic in the water. So because of this change of material, the water becomes more shallow at this position, which slows the waves down. So when the waves slow down, they change direction. As you can see over here, they were going straight, and then when the object came, they turned into this direction. So let me explain refraction a little bit. The waves keep oscillating up and down at the same rate. So they oscillate up and down at the same rate. By this I mean the same frequency. So when they slow, the wave fronts close up on each other. So they are tight, which means that the frequency has been increased. So this follows from the wave equation we learned. As the frequency is unchanged, a decrease in speed must cause a decrease in wavelength. So from this diagram, we can see that if the wave fronts close up on each other, their direction of travel must change as well, unless they are traveling at right angles to the boundary. So in this example, the boundary is not at right angles to this wave. The wave that is like this. The wave fronts are like this, they're straight, but the boundary of the plastic is laid like this. If the plastic was laid vertically as well, the same direction of the waves, then there would have been no change in direction. The waves would have just slowed down, which means the wavelength must have changed, but the direction would not have changed. Frequency means number of oscillations per second. Wavelength means distance between wave fronts, and speed means distance per second. Distance divided by second. So now that we've understood refraction, we're going to understand another wave effect, which is called diffraction. So in this wave effect, the waves bend around the sides of an obstacle or spread out as they pass through a gap. So as you can see here, we have this boundary. So these waves are like this and we have a boundary, but we have a small little gap over here. So when the waves pass through this boundary, they bend around the sides of this obstacle. So they spread out as they pass through this gap. This effect is called diffraction. So diffraction is only significant if the size of the gap is about the same as the wavelength. Wider gaps produce less diffraction, as you can see here. So we have a bigger gap here and the diffraction is less compared to this one. We have a smaller gap here. So it is only significant if the size of this gap is about the same size as the wavelength. So this is diffraction. So I believe you have understood refraction, reflection, and diffraction. Another point to remember about diffraction is that diffraction mainly occurs at each edge. So longer wavelengths would produce more diffraction. Now let's move ahead on to looking at some wave evidence. So we're going to see how refraction, refraction, diffraction, and reflection occur in our daily life. So A. Light reflects from mirrors. Sound reflects from hard surfaces. This is a very good example of reflection. So we're not only talking about water here, we're also talking about light and sound. They also travel as waves. So light reflects from mirrors. We have seen that, haven't we? And sound reflects from hard surfaces. So that is how we get echoes. So echo is an example of sound reflection. B. Light bends when it passes from air into glass or water. This is an example of refraction. So yes, it does bend, we can see that. So this is the example of refraction. C. Sound bends around obstacles such as walls and buildings, which is why you can hear around corners. So this is an example of reflection. So we have a corner of a building and we have two streets around this building. So if people are talking on one street, the people on the second street would hear them. So that is an example of reflection of sound. That sound bends around obstacles such as walls and buildings, which is why we can hear around corners as well. Okay. D. Light spreads when it passes through tiny holes and slits. This suggests that light waves must have much shorter wavelengths than sound. So sound does not spread when it passes through tiny holes or slits, but light does. So this suggests that light waves have shorter wavelengths than sound. That is why they are able to diffract. Like we have keyholes in our doors. If the room is dark, when we close the door, light from outside the room passes through the tiny hole and spreads. So you may want to try and look it for yourself. E. Some radio signals can bend around very large obstacles, such as hills. So this suggests that radio waves must have long wavelengths. So this is an example of reflection. This squashes and stretches the air in front. And as a result, a series of compressions, which are the squashes, and rarefactions, which are the stretches, travel out through the air. These are sound waves. When they reach your ear, they make your eardrums vibrate and you hear a sound. We can even hear the compressions or rarefactions, as I was talking before. They can be heard and they can be felt, the vibrations. So this was some wave evidence of these effects: diffraction, refraction, and reflection. So here we have some examples of transverse and longitudinal waves. In longitudinal waves, we only have sound waves. So this is the only example of longitudinal waves. But of transverse waves, we have many different examples. We have water waves, we have infrared rays, ultraviolet rays, microwaves, gamma rays, X-rays, and light. All of these are grouped up into electromagnetic waves, including light as well. So these are all electromagnetic waves, and they are all transverse waves. Now let's look at the nature of sound waves. So we have these 5 points that I'm going to describe in detail. Firstly, we have sound waves are caused by vibrations. So yes, any vibrating object can be a source of sound waves. As well as loudspeaker cones, examples include vibrating guitar strings, the vibrating air inside a trumpet, and the vibrating prongs of a tuning fork. You must have seen all of these instruments before. Also, when hard objects such as cymbals and steel drums are struck, they vibrate and produce sound waves. In guitar, we have strings that vibrate, and in a trumpet, we have air which vibrates. The prongs of a tuning fork vibrate, which produces sounds. The second point of sound waves is that they are longitudinal waves. So the air oscillates backwards and forwards as the compressions and rarefactions pass through it. When a compression passes, the air pressure rises, and when a rarefaction passes, the pressure falls. So the distance from one compression to the next is the wavelength. I just said it before, and I'm saying it again, that we can even hear the compressions and rarefactions. The third point is that sound waves need a material to travel through. This material is called a medium. Without it, there is nothing to pass on any oscillations, so sound cannot travel through a vacuum. A vacuum is basically completely empty space, neither any objects nor any air in this space. The fourth point is that they can travel through solids, liquids, and gases. So most sound waves reaching your ear have traveled through air, but you can also hear when swimming underwater, and walls, windows, doors, and ceilings can all transmit sound. The last point to remember is that sounds can be reflected, refracted, and diffracted. So an example of diffraction of sound is when you hear someone through an open window, even if you cannot see them. That is because sound waves are diffracted by everyday objects, so they spread through gaps or bend round obstacles of similar size to their wavelength, typically from a few centimeters to a few meters. Okay, so these were the 5 points that we have to remember to understand the nature of sound waves. I hope it is all clear to you. So, we're going to move ahead on to how we display sounds. So yes, sound waves can be displayed graphically. We do this by using a microphone and an oscilloscope. When sound waves enter the microphone, they make a crystal or a metal plate inside it vibrate. So the vibrations are then changed into electric oscillations, and the oscilloscope uses these to make a spot oscillate up and down on the screen. It moves the spot steadily sideways at the same time, producing a wave shape called a waveform. So here we have the oscilloscope. This is the point which oscillates up and down and also side to side. So it goes here, it changes. It moves horizontally as well as vertically. If it was only moving vertically, then the point would just move up and down at the same point. But when it moves the spot steadily sideways at the same time, the spot makes a wave shape like this. So this wave shape is called a waveform. So this is the oscilloscope and this is how it works. So now that we've understood this oscilloscope and how we display sounds using microphones and oscilloscope, we're going to move ahead on to understanding reducing sounds. So, hard surfaces reflect sounds and can cause echoes. In large rooms and halls, the soft materials in curtains, carpets, and padded furniture help reduce the problem by absorbing the energy in sound waves. The bricks, wood, and steel used in buildings are all good transmitters of sound waves. So, to stop unwanted sounds getting in or passing from one room to the other, panels backed with foam or fiber wool can be used to cut down sound transmission. So this is one way we can cut down sound. We can also have double or even triple glazed windows to reduce sound transmission. So glass is a good transmitter of sound waves, but glass sheets with an air layer sandwiched between lets much less sound through. Now we're going to look at the speed of sound. In the air, the speed of sound is about 330 meters per second or 760 miles per hour. So, here we have 3 points to remember. Firstly, the speed of sound depends on the temperature of the air. Sound waves travel faster through hot air than through cold air. Secondly, the speed of sound does not depend on the pressure of air. So if the atmospheric pressure changes, the speed of sound waves stays the same. Thirdly, the speed of sound is different through different materials. So sound waves travel faster through liquids than through gases, and fastest of all through solids. So now, let's look at how we can measure the speed of sound. So here we have an experiment to measure sound. So we have two microphones here which are connected to this timer. The distance between these microphones is 100 meters. So one microphone, the first microphone, starts the timer, and the second microphone 1.00 meters. So what happens is that a sound is made by hitting a metal block or plate with hammer. When the control unit receives a pulse of sound from the microphone, from microphone A, this one, it starts the clock. When it receives a pulse from microphone B, which is this one, it stops the timer. So if B is 1.00 meter further away from the source of sound A, and the clock records a time of 3.0 milliseconds, which would be 0.003 seconds, then we can find out the speed of sound by this equation. Speed of sound is equal to distance traveled divided by time taken. So we divide 1.00 meters by 0.003 seconds, and we will get 330 meters per second. So this is the equation of speed. So we can find out the speed of sound by this experiment. And the speed of sound is 330 meters per second. Or we can also call it 760 miles per hour. So when the sound is made, the first microphone receives it. It gets a fraction, it's like a fraction of a second that the two microphones receive the sound. But the microphone A receives it first, so it turns the timer on, and when the microphone B receives the sound, it turns it off. So it's a very short time interval, which is of 0.003 seconds, 3.0 milliseconds. So this is then divided by the distance, which is 1.00 meters, and we divide them and we get 330 meters per second. So this is how we measure the speed of sound. So we have understood the speed of sound, how we display sounds, and how we reduce sound. So we can move ahead on to now understanding the refraction of sound. So, distant trains and traffic often sounds louder and closer at night. The reason for this is that during the night time, when the ground cools quickly, air layers near the ground become colder than those above. So sound waves travel more slowly through this colder air. This is refraction of sound. A change in material makes a change in the wavelength of sound waves. So sound waves travel more slowly through this colder air. So as a result, waves leaving the ground tend to bend back towards it instead of spreading upwards. So a bending effect like this, caused by a change in speed, is called refraction. A change in direction also occurs, just like we read before in refraction, that waves then tend to change in their direction. So instead of spreading upwards, they tend to bend back towards the ground. So this type of bending effect is called refraction of sound. So this was refraction of sound. Now we're going to look at echoes. So hard surfaces such as walls reflect sound waves. When you hear an echo, you are hearing a reflected sound a short of time after the original sound. The time the sound takes to travel to the wall and back again is the echo time. So we must have heard echoes, of course. We say something and then we hear the same thing back. So this is called the reflection of sound. In normal words, we call it echoes. So hard surfaces reflect, such as walls reflect sound waves. So when you hear an echo, you are hearing a reflected sound a short of time after the original sound. So the time the sound takes to travel to the wall and back again is the echo time. So we can use the speed of sound equation again to measure the echo time as well. So speed of sound is equal to distance traveled divided by time taken. This equation is going to turn into speed of sound is equal to 2 multiplied by distance to the wall divided by the echo time. So if we are 2 meters apart from a wall, that is going to be the distance to the wall, and this distance is going to get multiplied by 2 because sound is reflected, so the distance is multiplied by 2. And then the echo time, how much time the sound took to travel to the wall and back again, that would be divided by this value, and we will get the speed of the sound. In the same way, we can rearrange this equation and find the echo time as well. For that, we would have to divide the distance with the speed and we will get the echo time. So if the speed of sound is known and the echo time is measured accurately, the distance to the wall can be calculated from the equation. In simple words, we just rearrange the equation. So this principle is used in several devices. Here we have some. So the echo sounder is a device. This measures the depth of water under a boat. So what it does is it sends pulses of sound waves towards the seabed and measures the echo time. So the longer the time, the deeper the water. So we know the speed of sound and we find out the echo time. Multiply both the values, which will give us the measurement of the depth of water. Then we have the radar. This uses the echo sounding principle, but with microwaves instead of sound waves. We're going to look at echo sounding in this chapter as well, but not right now. So this uses the echo sounding principle, but with microwaves instead of sound waves. It detects the positions of aircraft or ships by measuring the echo times of microwave pulses reflected from them. So this is a very interesting instrument. It detects the positions of aircrafts and ships by measuring the echo times of microwave pulses reflected from them. Okay, then we have parking sensors. These set off warning bleeps when a car is getting too close to an obstacle. Some work like a radar and some use sound pulses. Okay, so this was all about echoes and the several devices that use the principle of echoes. Now that we've understood refraction of sound and the reflection of sound, we can move ahead onto understanding frequency and pitch. So sound waves are caused by vibrations. For example, the rapid backwards and forward oscillations of a loudspeaker cone. The number of oscillations per second is called the frequency. It is measured in hertz. We've read this before. Well, different frequencies sound different to the ear. You hear high frequency as high notes. Musicians say they have a high pitch. And you hear low frequency as low notes. They have a low pitch. So the human ear can detect frequencies ranging from about 20 Hz up to 20,000 Hz, although the ability to hear high frequency decreases with age. Let me tell you about octaves. So musical scales are based on these. These are called octaves. If the pitch of a note increases by 1 octave, the frequency doubles. So if two steady notes an octave apart are picked up by a microphone and displayed on the screen of an oscilloscope, as the higher note has double the frequency of the lower note, the peaks occur twice as often and are only half as far apart. So this was all about frequency and pitch. Now we're going to move ahead on to understanding the timbre or quality of sound. So middle C on a guitar does not sound quite the same as middle C on a piano, and its waveform looks different. So we say that the two sounds have a different quality or timbre. So each sound has a fundamental frequency giving middle C, but other weaker frequencies are mixed in as well. These are called overtones, and they differ from one instrument to another. As you can see, all of these instruments, flute, clarinet, oboe, and saxophone, are playing the same note, but their frequencies are different from each other. The fundamental frequency is going to be the same, but the overtones of each of these instruments are different. So when they add up to the frequency, they make a different waveform. So the final waveform of saxophone differs from the final waveform of flute. This is because of the overtones of these instruments. So this was all about quality. The human ear can detect sounds up to a frequency of about 20,000 Hz. Sounds above the range of human hearing are called ultrasonic sounds or ultrasounds. So 50,000 Hz, for example, a human cannot hear this much sound. This comes into ultrasound, but dogs can hear this. Dogs can hear up from 20 Hz to 50,000 Hz. Humans can hear from 20 Hz to 20,000 Hz, and bats can hear from 20 to 120,000 Hz. So they have the biggest sound range. Sounds above 20,000 Hz are called ultrasonic sounds or ultrasound. Now let's look at some of the uses of ultrasound. First, we have using ultrasound for cleaning. So using ultrasound, delicate machinery can be cleaned without dismantling it. The machinery is immersed in a tank of liquid. Then the vibrations of high-power ultrasound are used to dislodge the bits of dirt and grease. So in this way, the machinery gets cleaned up nicely and it doesn't get dismantled as well. In hospitals, concentrated beams of ultrasound can help be used to break up kidney stones and gallstones without patients needing surgery. Well, this is one use of ultrasound. The second use of ultrasound is echo sounding. So ships use echo sounders to measure the depth of water beneath them. An echo sounder sends pulses of ultrasound downwards towards the seabed, then measures the time taken for each echo to return. We read about this echo sounding principle when we were reading about echoes and reflection of sounds. An echo sounder sends pulses of ultrasound downwards towards the seabed, then measures the time taken for each echo to return. The longer the time, the deeper the water. For example, if a pulse of ultrasound takes 0.1 second to travel to the seabed and return, and the speed of the sound in water is 1400 meters per second, then the distance traveled would be equal to speed into time. And we will get 1400 meters per second multiplied by 0.1 seconds, and we get 140 meters. So 140 meters is the depth of the water. But the ultrasound has to travel down and back, which means that the distance would be the double of the actual distance. So the depth of water is going to be half multiplied by 140 meters. Basically, we will divide 140 by 2, half the value of this, and we will get 70 meters. So this is going to be the depth of the water surface. Most echo sounders scan the area beneath them. They sweep their ultrasound beam backwards and forwards and from side to side. A computer displays the depth information as a picture on a screen. This is such a cool thing, isn't it? Well, this was echo sounding. I hope you have understood it, and it's pretty simple. An echo sounder just sends pulses of ultrasound downwards towards the seabed and then measures the time taken for each echo to return. The longer the time, the deeper the water. So then we apply the equation and we find the distance traveled. Then we divide the distance with 2 to half it, and we get the real distance, the real height. Now let me show you this bat here. This bat uses ultrasound to locate insects and other objects in front of it. It sends out a series of ultrasound pulses and uses its specially shaped ears to pick up the reflections. The process is called echolocation, and it works like echo sounding. Bats can hear up to 120,000 Hz of frequency, which means that they can also hear insects. Well, let's move ahead on to understanding metal testing. So, the echo sounding principle can be used to detect flaws in metals. A pulse of ultrasound is sent through the metal. If there is a flaw by which we mean a tiny gap in the metal, 2 reflected pulses are picked up by the detector. So the pulse reflected from the flaw returns first, followed by the pulse reflected from the far end of the metal. The pulses can be displayed using an oscilloscope. The trace on the screen is a graph showing how the amplitude of the ultrasound varies with time. So this is another use of ultrasound. We test metals by this. Test if there are any flaws like tiny gaps or cracks in the metal. Now, lastly, we have scanning internal body. So here you can see the pregnant mother in the photograph is having her womb scanned by ultrasound. Again, the echo sounding principle is being used. A transmitter, the one this woman is holding, sends pulses of ultrasound into the mother's body. The transmitter also acts as a detector and picks up pulses reflected from the baby and different layers inside the body. The signals are processed by a computer which puts an image on the screen. As you can see, this is such an amazing use of ultrasound. So this was all for today's chapter. In this chapter, we understood waves and sounds. We understood transverse waves and longitudinal waves. We understood the properties of waves. Then we understood the wave equation, which is pretty simple. Speed is equal to frequency into wavelength. And then we understood the properties of waves, which can be studied using a ripple tank. The properties of waves like reflection, refraction, and diffraction. We looked at some of the wave evidences of diffraction, refraction, and reflection in our daily life. Here we have the table of examples of transverse waves and longitudinal waves. We have all electromagnetic radiations in transverse waves as well as water waves. Longitudinal waves only have sound waves. And we saw the nature of sound waves. And then we understood how we display sounds graphically using a microphone and an oscilloscope. We saw how an oscilloscope converts a sound into a waveform. After this, we understood how we reduce sounds. In other words, we looked at echoes, the different things we do to stop unwanted sounds getting in or passing from one room to the next, to cut down sound transmission. Then we looked at the speed of sound, measuring the speed of sound, how we can measure the speed of sound, the small experiment, and then we understood refraction of sound. After this, we looked into more detail of echoes. We looked at the devices that use the principle of echoes. And then we understood frequency and pitch. We also understood the quality of a sound, the timbre. And lastly, we understood ultrasound. How we can use ultrasound for cleaning, for echo sounding. What is echo sounding? We looked at some animals and their range of hearings and how they use echolocations like the bat ear. We understood metal testing, how ultrasounds are used to test any flaws in metals. And lastly, we understood how ultrasound is used to scan internal body. So this was it for today's chapter. We have completed our 6th chapter successfully, and our next chapter is going to be rays and waves. So thanks for watching this video, and I'll see you in the next video.